What's up, meat wagons? Today we're gonna talk about your least favorite problem. No, probably your favorite problems. These ones are tight. I'm gonna be honest with you. These are some of the problems that we've kind of like set aside just because we're like, you know what? Maybe. Are you sure you want to give these? Give? Holy smokes! I'm getting southern on you. Are you sure you want to give these to kids? I mean, this one killed Jimmy. Like, do you remember Jimmy? He's dead now because of these. You can't just hand these out to kids. But I said, nope, give them to the kids. So, we're going to talk about some big kid problems today. And we're going to do some math and magic. We're going to do some math trickery. And we're going to apply everything we know about solving systems of equations. We're going to apply everything we know about Newton's three laws. We're going to apply everything we know about force diagrams. It's going to be so cool. You're going to be like, wow. Like, you're going to feel like you've suddenly become some sort of like omniscient warlock who made a pact with a demon for unlimited power and the ability to see through time and space. Um, so, yeah, I mean, let's do it. Okay. Buckle up, kiss your mom goodbye. Tell her when you come back, you're going to be a grown woman or man or non denominational, whatever it is you think you are. So, all right, let's do it. Hey, no vocabulary. We're just going to use what we know to do some hard problems. So, this one says there are 3 blocks lined up on a smooth table. So, smooth, here we're saying no friction. But Mr. Barton, wouldn't the problem be harder and deepen my connection with my newfound power? Yes, you're right. However, the problem is left for an exercise for a reader. Someday that joke will be so funny to you guys, but not right now. The medium block, this one right here, has a mass of 4 kilograms. Let's label that 4 kilograms. The small block has a mass of 3 kilograms, and the large block has a mass of 6 kilograms. All right. The medium block is being pushed to the right so that the entire system has an acceleration of 2 meters per second squared. Find the contact force between each of the blocks and the applied force on the medium block. So this problem is one of the most classic examples of Newton's, guess it. Oh, you're right, the third law. And you have to write your L's in cursive. That's part of the practice. So what we're looking for is, because this block is a solid hunk of mass, and so is this block here, we want to know what is this contact force in between there. Same thing here. And then we want to know what is that force pushing on these blocks. We want to know all the different pushes between all the solid things in this setup. So this problem is an exercise in redundancy. What we're going to do is we're going to start with the thing with the least forces acting on it. Then we're going to work our way over through the system of blocks, looking at force diagrams the whole time, looking at systems of equations and sum of forces. So let's start with this green block. Let's do it in green so we know what we're talking about. The force diagram for this green block. We, of course, have weight down, and we, of course, have a normal force from the ground pointing up. These are equal to each other because Newton's first law. We're not accelerating up and down, so the up and down part of the forces have to be balanced. And it's accelerating to the right because we say we're pushing on this row of blocks and it's going to the right. And you could do this at home, right? You could get like a tissue box, a book, and maybe like your pencil box or something. And do people still have pencil boxes? Anyway, line 3 things up, push on one end, and all 3 of them will move together. You'll see. Believe me. So, and we have finally the normal force between these 2 boxes pushing to the right on this. So we're going to have, I'm going to put, maybe we should call it contact force. Are you more okay with that? Do you want normal force or contact force? Oh, okay. So I'll do contact force, just because we're going to have a bunch of normal forces. So force, contact, and we'll say large, small, on the large block by the small block. Okay. So this is going to be fairly straightforward to solve. We're looking in the x direction because that's the direction that the acceleration is in. This 2 meters per second squared, we're going that way, 2 meters per second squared. So we're interested in the x direction. So let's just look at our sum of forces in the x direction. Sum of forces in the x equal the contact force on the large block by the small block equals the mass of the large block times the acceleration. And this acceleration is the 2 right here. So now we can just plug in some numbers and find this. So the mass is 6 kilograms. The acceleration is 2. So this force, the force of contact between the large block and the small block, is 12 newtons. Okay, so we found this contact force right here. Now let's look at this middle block. Let's change to our pretty pink draw force diagram. So we have the weight down. It's a little bit smaller because it's a smaller block. We have the normal force from the ground up. And these are equal because still Newton's first law. We're not accelerating up or down, so the up-down forces should balance. Now, here's where things get tricky. This 4 kilogram block is pushing to the right on the 3 kilogram block. So we're going to put force contact on the small block by the medium block. And we're going to have backwards, it's running into the 6 kilogram block. So we have the third law pair here. 1, 2, 3, 1, 2, 3. Force contact on the small block by the large block. These are equal because of Newton's third law. So I already know this one, it's 12. So we're going to do the same process, write a sum of forces in the x direction for this middle block. Sum of forces in the x direction. We have the force contact on the small block by the medium block minus the force of contact from the on the small block by the large block equals MA. We know this value here, it's 12. We know the mass, it's 3. We know the acceleration. The whole system, all 3 pieces of it, are accelerating at 2 meters per second squared. So now we can solve this very easily to find this one. So this would be 6, and then we add the 12 over. So force contact on the small block by the medium block is 18 newtons. And there we go. We have all 2 contact forces between the blocks. The last thing we need to find is this force applied. So let's switch to teal. Force diagram. We have weight. We have normal force. We have this force is the third law pair. This one is pushing to the right on this one. This one's in the way, so it's pushing back on this one. So we're going to have a back force, force of contact on the medium block by the small block, and it's a third law pair. So 1, 2, 3, 4. 1, 2, 3, 4. Third law pairs. So they have to be equal and in opposite directions. Then this block is still accelerating to the right. So we have another force pointing to the right. That's the applied force, force A. Now we just set up this sum of forces one more time and solve for our applied force. So sum of forces in the x direction equals F applied minus the contact force on the medium block by the small block equals MA. The mass here is 4. The acceleration is still 2. This force we know because we just solved for it. It's 18. So this is 8. We add the 18 over to it. The force applied must be 26 newtons. Okay. One more thing I want to show you before we go, just to show you a trick for solving for this applied force without having to do all the work that we just did. There's a shortcut. How much total mass is there? 4 plus 3 is 7 plus 6 is 13. So if we think about it as one big mass, 13 kilograms, being pushed to the right, our force diagram would be the weight, the normal force, and the applied force. So we have the total amount of mass. The sum of forces in the x direction equals just the applied force, equals MA. M is 13, A is 2. Force applied, equals 26 newtons. So you can take all three of these and just smush them together and pretend it's one big force or one big mass, and then you'll be able to do the problem a little faster. That still doesn't tell you the contact forces, but they're not too bad to find. So this is one of the most classic third law problems in existence. You'll probably see this if you go to college. It's pretty common. It's pretty much how they teach the third law. So there you go. Your first big kid problem. Do you guys feel it? Do you feel that tingling in your toes right now? That's not boredom and lack of blood flow to your legs because you've been sitting for so long. That's the physics superpowers coming in. All right. Let's spread that tingle all the way up to your hips. Stack of boxes. This is the problem in that really long friction set of notes that I showed you a glance of and then said, no, back up. That's too long. The video's too long. Call it a day. Pack it up. We're going home. And you're going to say, Mr. Barton, you withheld warlockery from me because of the length of the wisdom you were imparting? Sorry, kids. That's sometimes the way it's got to be. So let's go ahead and solve this problem. So there are two boxes, obviously, on a rough surface. Friction applies. One resting on top of the other, obviously. The bottom box has a mass of 0.5 kilograms. The top box has a mass of 0.3 kilograms. The coefficients of friction between the bottom box and the ground are 0.4 for static and 0.2 for kinetic. The coefficients between the boxes themselves are 0.2 for static and 0.1 for kinetic. Find the maximum acceleration of the system before the top box begins to slide off the bottom. We're going to amend this. Comma. And the maximum applied force. Just to make it fun, because I realize this question is incredibly easy. So let's answer that question right now. So let's think about it. If I push on this box is going to start to slide that way. If I push too fast or too hard, right? And I encourage you to do this. Go get two things, make them pretty light. I wouldn't use like your dad and your dog, right? Pick like 2 tissue boxes or something. Stack them and push really hard on the bottom one. See if you can slap the bottom one out from under the top one. I bet you can, as long as they're light. If you have two things that are kind of heavy and like sticky, like textbooks with like a real glossy cover don't work super well. But maybe like regular paper books, as long as they're kind of a matte finish, would be fine. Or tissue boxes, this works really easily with. So let's figure out what is the maximum acceleration. And we want to know when the top box slips. So if we push this, it's going to slide out. That means this bottom surface is going to slide that way. So this top box is going to be frictioning that way. Okay, so the friction from the top box on the bottom box is to the back. but friction has a third law pair. If I apply friction on you, you apply friction on me. And Newton's third law says opposite directions. So this top box pulls back on this bottom box. This bottom box, the friction pushes this one forward. Let's look at a force diagram of the top. So we'll go to this nice pink color. It's probably not pink. One of you is like a color enthusiast, screaming, ripping your hair out. Mr. Barton, that's not pink. Don't say it's pink. We have weight of the box. We'll call this weight. We'll call this box 1 and this box 2. Weight 1. And we have normal force. I'll just call it 1. Okay. So if we push this slowly, this box will go that way. It'll stay on it and it'll accelerate forward. That means that forward force from friction must be pointed to the right. Friction, it's not sliding off this. We want to find the maximum acceleration before the top box starts to slide off. It's not moving. If it's moving with it, static, because they're stuck together. Okay, so this is a very simple force diagram. So let's go ahead and solve this for let's look in the x direction, shall we? Okay, so we have force of static friction equals mass times acceleration. The equation for our static friction is mu n. And in this case, it's this normal force. It's the normal force where the objects are touching. So this is the normal force of the bottom box pushing up on the top box. So this is going to be mu static n1 equals ma. We're looking for a. So let's plug in the rest of these. We should know them. And we have to calculate. It's the same as weight. So we could replace this with mu s equals mg. Okay. Now we're just plugging in numbers. So the bottom box and the top box, let's see, top box has a mass of 0.3. So we're going to have 0.3. G is 10 for us equals 0.3. Oh, isn't it crazy? Those cancel. Right. A. And then mu s, bottom box on the ground. Nope. Coefficients between the boxes, 0.2. Okay. So 10 times 0.2 is 2. A is 2 meters per second squared. So the maximum acceleration this top box can feel, given the numbers we have, is 2 meters per second squared. Okay, easy, we did it. Now, let's find this extra bonus question. Find the max applied force. So we're pushing on the bottom box. So now we have to do the hard part, and we have to look at the force diagram for the bottom box. So let's see. We've got friction with the ground pushing that way. We've got friction with the top box pushing back. We have the applied force going to the right. We have weight down. This top box is also pushing down. And then we have the normal force up here. So there's 1, 2, 3, 4, 5, 6 forces on this. That's what makes this a big kid problem. So let's draw that force diagram. We have weight 2. We have force applied. We have friction. The bottom box is sliding on the ground. Kinetic. So this is the friction between the ground and the bottom box. We also have the static friction between the top box and the bottom box. We have the top box pushing down on the bottom box. That is the third law pair to this. So I'm going to go ahead and put N1 here. And then we have the normal force from the ground pushing up. I'll call that N2. So let's see. 1, 2, 3, 4, 5, 6. We have all our forces. Now we're going to do our sum of forces in the x direction because we're looking for that right there. So sum of forces in the x direction equals our force applied minus our friction kinetic minus, because it's in the negative direction, our friction static with the top box equals the mass of the big box times the acceleration. This acceleration is our max acceleration from here. Okay, if we accelerate faster than this, then we figured out that the friction between the top and bottom box isn't strong enough, and then the top box is going to start to slide backwards. It won't have enough friction to keep it on. Okay, now we're going to start substituting. Force applied is what we're looking for. We don't really care if that stays as a variable. Friction kinetic. This is the sliding friction of the bottom box. So we're going to have mu k. We have to make sure we get the right one because there's 2 in this problem. Times N2. Okay. That's the ground pushing up on the box. Minus mu s. And then, or actually, we know mu s, don't we? It's right here. It's 10 times 0.2 is 2 times 0.3. 2 times 0.3 equals 0.6. So this is actually 0.6. We can just plug that in. Equals mass of the bigger box, box 2. The bottom box has a mass of 0.5 kilograms. So 0.5, A is 2. All right, we're getting there. We're plugging stuff in. So we could simplify this. This is 1. All right. Our normal force 2 is equal to these 2 forces combined. So we can make a substitution there. We can say N2 equals N1 plus weight 2. N2 equals M1G plus M2G. So it's actually, G. We could factor the G out if we want. N2 equals the sum of the masses times G. So what are our 2 masses? 0.3 and 0.5. So this is 0.8 times G is 10. So this is 8 newtons. So N2 is 8. So we have force applied minus 8 times, what's our kinetic? We're almost there. The coefficient between the boxes? No. The coefficient of friction between the bottom box and the ground, that's what we're looking for. Mu static? No, we're sliding. 0.2. 0.2 minus 0.6. All right. So close. 0.2 times 8 is, what is it, 1.6? Minus 0.6 equals 1. Negative 1.6 minus 0.6. This is negative 2.2 equals 1. Add the 2.2 over. Our force applied equals 3.2 newtons. Bingo. We did it. Oh my goodness. What a sweet problem. Did you see that? I'm serious. Go show this to someone. This is so tight. Look at this. Almost a full page of work. Substitutions everywhere. Look at this. 6 forces on a single force diagram. Go tell your mom you deserve a brand new pair of J's right now. Mom, do you see what you're making me do? I deserve to be rewarded. I want a new pair of shoes. But say it politely, like she's your mom. You should be nice. All right. So there's that problem. On to the last problem. Wait, where have we seen this before? Is that the lab? Is that the lab? It is the lab. So this lab has a name. The name of the lab is a modified Atwood machine. If you really want, we can look at an Atwood machine, the non-modified version. That one's pretty cool too. But we'll look at the modified one because it's a little bit more straightforward. The unmodified one is a real big kid problem. Maybe that'll be like a challenge problem or something. That'd be fun, huh? So we have a mass of 1 kilogram is at rest on a frictionless surface. That must be this one. 1 kilogram. The mass is tied to a 200 gram mass By very light, that means we get to ignore the mass of the string. That's good for us because if we don't get to ignore it, oh boy, that's a problem and a half. You actually probably can't solve that problem without calculus. It's hard. So very light string, and the string is run over a frictionless pulley. Good. This thing, super smooth bearings. This thing's got black cat bearings or something in it. Those are the really nice bearings I used to have in my skateboard as a kid. They're super nice. Those things would spin forever. The entire system is released. Find the acceleration of the cart. All right. So they don't give us much. They say there's no friction anywhere. This mass is 1 kilogram. This mass is 0.2 kilograms. 200 grams, we move the decimal 3 places left to get kilograms. So 0.2. All right. So you might say, Barton, I don't know where to begin. This is crazy. You want me to do what? So let's go ahead and just draw some force diagrams. Let's look at the force diagram for this hanging mass and for this mass up here. So starting with the hanging mass. Well, it's got weight down. Okay. And then it's got this string attached to it. So it must have tension up. All right. Cool. No normal force because it's not resting on any solid surfaces. Let's go look at this mass. So this mass, we've got weight down. We've got the normal force up. And then we've got the tension right here is pulling it that direction. We would assume, right? If I pull down here, this rope will pull that way. So tension to the right. All right. Now, what do we know? Well, we know the normal force and the weight must be equal. Okay. Are the weight and the tension equal? What do you think? Say it right now. Turn to your dog and say, dog, here's what I think. Oh, you're right. They're not equal. and now you're turning to your dog. Dog, I'm such a dummy. Because you told them they were equal. But we'll forgive you. We know they're not equal. A, because it's asking us to find the acceleration. If they're equal, it won't accelerate, right? So that's not good. B, think about it. If you let go of this, is it going to just start moving on its own? Yeah. So that means your velocity is changing. It goes from not moving, which is velocity equals 0, to moving. So obviously it's got to accelerate if the velocity changed. So if the velocity changed, we have an acceleration. And because of Newton's second law, if the sum of forces are not balanced, it equals ma, and we have an acceleration. So these are not equal. However, this is one rope, and this is super frictionless, so it's not going to hold back the string. Strings have constant tension throughout them. So we can say that this tension and this tension are the same because of Newton's third law. However hard the rope pulls on this, it must pull back that hard on this because it's the same rope and it's pulling, right? That's the third law pair, the two tensions. Okay, so we've got our force diagrams. They're pretty simple, right? Not that intimidating. Now we have to solve this problem, and there's one kind of mental leap we're going to have to make. So let's look at the sum of forces in the y direction here. We'll look at maybe the sum of forces in the x direction here because that seems to be the important bit. That's the thing that's unbalanced and making it accelerate. So let's look at our sum of forces. I'm going to say up is positive and to the right is positive. So the sum of forces in the y direction equals tension minus weight equals ma. And then I'm just thinking if this is going to work out or not. There's, I think, sort of a trick here, but we'll see. We'll see. The signs might get a little goofy, but we'll be careful. Here, the sum of forces in the x direction equals just tension equals ma. All right, let's call this one mass 1 and this one mass 2. So this is mass 1 here. This is mass 2 here because it's that object. All right, so we're looking for the acceleration. Which acceleration? This one or this one? Well, these objects are connected, right? This object is going to accelerate that way. This object is going to accelerate that way. Oh, okay. I think I just found the thing we have to be careful of here. But I'll show you. So these are the same acceleration. They're going to move together. So just like in this problem, all the accelerations were 2 because this box is accelerating with this box with this box. This box and this box are connected and they're going to accelerate together. Okay. Let's be careful here. What direction is this acceleration? It's going to accelerate that way, in the negative direction. This is going to accelerate that way in the positive direction. So if this is A1 and this is A2, we're going to say A1 equals negative A2 because it's the acceleration, but this one's negative and this one's positive. If you want, you could say down is negative here or down is positive, and then you could say A1 equals A2. That would work, but you have to be very careful with the signs and keep everything very formal. So we're looking for A. So we know these tensions are equal. Let's go ahead and take this and substitute it into this tension and see if we can solve the problem. So we have M1, A1 minus weight. This is weight 2 of that object equals M2A2. All right. We're going to subtract this over. So we have negative M2G, right? Because the equation for weight is mass times gravity, equals M2A2 minus M1A1. But we know A2 equals negative A1. Right? Because they're accelerating together and directions cause the negative sign. So let's substitute that. This is going to be M2 negative A1 minus M1 A1 equals negative M2G. We're looking for A. So let's factor out an A from here. So we're going to have negative M2G equals A negative M2 minus M1. And then we're going to divide both sides by this term. Negative M2, negative M1. Okay, these cancel. We get A equals negative M2G. Let's factor a negative out of this. Negative 1, M2 plus M1. The negatives cancel. So our acceleration equals M2G divided by M1 plus M2. And now we can just plug in our masses and G. So we have 0.2 and 1. So we have 0.2 times 10 divided by 1 plus 0.2 is 1.2. So we have 2 divided by 1.2. And then we grab a calculator. We grab a calculator. We keep grabbing the calculator. 2 divided by 1.2. A equals 1.66 repeating. We can round to 1.67 meters per second squared. Okay, let's again, take a step back and see if there's maybe a shortcut or a trick to this problem, because this is another very famous problem that you will study when you go to a university and take physics, because you found a love for physics, not English, for physics, and you decide you're going to major in physics. When you grow up, you want to be a physicist because this class is so tight. And even if you don't want to be a physicist, maybe you want to be a physics teacher. That'd be cool. All right. So let's go ahead and look at this, right? Or actually right here. Let's look at this. Acceleration equals m2g divided by the sum of the masses. Okay. m2g, what is that? That's the weight of the object. That's this thing. That's this weight right here. This is m2g divided by both masses. That seems so we have a force divided by mass. Hang on a second. A equals F divided by M. This is Newton's second law. Right? Yeah, totally. Multiplied by M, F equals MA. Oh, that's crazy. Okay, so let's think about this. M on the bottom, this is the total mass of the system. It's both masses together. Okay? This is the weight of that block that's hanging. What is the force that's making the whole system move? The hanging mass, the weight. Gravity's pulling down on it, so the whole system accelerates. This is another case where we're looking at the total mass of the system. And in this case, we know the force being applied, the weight of that block, and we're solving for acceleration instead of knowing acceleration and mass. That's crazy. So if we want to do another problem, right? We could, let's change these. Let's make them 2 and I don't know, also 2. Let's make them both 2, right? It's acceleration equals the force, so 2 times g, right? The gravity from the hanging mass, divided by the total amount of mass. 4, 20 divided by 4, 5 meters per second squared. That's so crazy. So this is another one of those problems where we can simplify it by saying, what's the total amount of mass? What's the force being applied? This will be the acceleration of the whole system. So we can look at it in an aggregate way instead of having to do this big mess of algebra here. But it's important that we understand how to set up this big mess of algebra so that we can get nice results like this. This is called deriving a general solution. It's one of the most satisfying things in physics, I think. You get to look at a problem, study it, be very rigorous with your problem solving, and then you find a very pretty solution that describes the entire system very, I don't want to get too poetic on you, but it brings a tear to my eye, honestly. It's so beautiful. It's just like, oh my God, math. Ooh, makes me swoon a little. So there's 3 big kid problems. So you should be tingling all over by now. You should be going, whoo, I feel like what is that? Is that knowledge sinking in? Is that understanding the way the whole universe works sinking in? I think it is. If you have questions, be sure to let me know. Otherwise, have a great rest of your day.